one right here, you know, like how would you integrate it and don't and try to look at it a little bit more carefully than just saying it's power rule. There's a bit more to it here.
Would u sub work?
It's actually the bounds here that are the issue. We didn't get into one of these last night. Do you remember improper integrals?
Yes.
So the issue with this one is that it is not defined at 0. So you have to actually break this up into two integrals, -1 to 0, plus 0 to 1, like this. And you have to use that limiting process for it.
Okay.
So I mean, I can find some problems like that if you know, if you think that would be good. You know, this one, if you recall, you would carry it out by using a bound like B for these. And this one actually, you find it actually diverges. But another one that you know, you might see on an exam is well, let me keep looking here. Is this okay doing it kind of this way? Because I've got another problem I can pull up here. I'm going to snip this one in, and it's kind of like last night. Just give me 30 seconds. Take a look at that, and I'm going to ask you how you might solve this when I get back. I'll be right back.
Okay.
All right, I am back.
All right.
How what do you see here? What's
So this is a trig integral.
It's a product of trig functions.
Mm-hmm. So it's like one of those if n is odd, it is even.
Exactly. Yeah. So in this case, it is n is odd.
Right.
The sign, you know, you got n equals 3 and m equals 2. So it says strip one sign out. So we'd make this sine x. And then there's really a sine squared here. But it says replace sine squared with 1 minus cosine squared. So this becomes 1 minus cosine squared x. And then the next part is really important. The u is cosine x. So your du is minus sine x dx. And of course, u squared is cosine squared x. So this becomes the integral sine x 1 minus u squared, because cosine squared is u squared. We've got another cosine squared here. So we're assuming that's a u squared there. And then dx is du over minus sine x. And these cancel. This negative would go with the inside here. So you would actually just change it to u squared minus 1 times u squared. And you would you know, integrate from here.
Okay.
You have time, like what I would do is do one where it's odd and then do the other where you flip it, like sine squared cosine cubed, and do the other perch.
Okay.
You know, time permitting, because I mean there's so much here. You know, how do you even do that? So here's another problem from and again, this one's actually from University of Colorado at Boulder. Again, it's like, well, how would you begin a problem like this? Like, what's your math intuition telling you on this one?
Is this a partial sum?
It's partial fractions. Yeah.
Partial fraction, yeah.
This one's probably more complicated than you would get, but it's good that you can identify that because it really is important here.
Right.
Any chance your final exam is multiple choice?
No.
Okay. So, the reason I ask is this one was a multiple choice problem, but I can clear those out and we can just look at this one. Set up, but not evaluate, do not evaluate. This actually looks a lot like the one that we were doing last night. If the area of the surface obtained by rotating about the x-axis. Okay. Do you have well, do you if you don't have it, I'll write it out here. It's the integral of 2 pi y square root 1 plus dy dx squared dx, because it's asking for the area of the surface.
Right.
Okay, so if you this goes in here, your bounds go from 0 to 1. And then the last thing is you have to take a derivative of this, come off the side here, y prime is 2e to the 2x, then you square it and you get 4e to the 4x. Remember, when you square an exponent, you multiply. So it becomes root 1 plus 4e to the 4x dx, something like that.
Now, what's the case if it is rotating about the y-axis?
Yeah, so let's do the same thing here, and let's go y on this.
You put the equation in terms of y, don't you?
You solve for x, so x
Right, yeah.
equals 1/2 natural log of y, and then you have to change your bounds. So you actually end up doing this in calculus 2. I'm sorry, calculus 3. When you do double integrals, you need to put that 0 in there. So e to the 0 is 1.
Right.
And then e to the 2 times 1 is e squared. So when you go y-axis, it's integral 1 to e squared 2 pi, and then it's x, but x means as a function of y, square root 1 plus, now your derivative, your x prime is 1 over 2y, and then x prime squared is 1 over 2y squared. So it's 1 over 4y squared, like that, dy.
Okay. All right.
Okay, so I mean, this other one I have found, this one's at BYU. I don't know why I'm favoring the West, but maybe the track internet gets there faster. I don't know, but this one, reasonable. So this is totally reasonable to ask on a final exam. There's nothing like overly complex about this, but the real question is like, what kind of integral is it? And you start with u sub, and you made that really good point yesterday that it's generally a composition of functions. This one is not a composition. There's not an inside function, and then integration by parts. Not generally, it's a product. Okay, so this is kind of the progression you might go down, and then we talked about trig substitutions, products of trigs, partial fractions, and so on. What stands out to you here in terms of
integration by parts?
Yes, this is an integration by parts. What is your u and what is your dv if you were to do this?
Would your dv be sine x?
Yes, and your u is almost always the polynomial.
Okay.
So you go down this this road here and get and keep going. uv minus integral v du. This right here tells you you're gonna do integration by parts twice. Because it's a square. And because it's a definite integral, you have to evaluate your UV at the endpoints. Do you remember when does that make sense? Is that
Yes.
clear? Okay. I probably wouldn't have you evaluate in integration by parts twice with a definite integral, maybe with one, because it just adds another like layer of complexity that's like not part of the solution, but
Right.
you know, that's what it is. Okay. This one is a bit tricky because I think it looks like something that it isn't. But let's take a look here. At it. No, okay, yeah, maybe we can look at it. I don't want you to. So.
Now, at first, I'm thinking trig substitution.
Yeah, it sure looks like it. Like it looks like it's the. Let me pull it up here. I think it's tan.
Yeah, I was thinking tangent.
Yeah, so it looks a lot like the form where it's actually it's written this way: a squared plus b squared x, and then that produces x equals a over b tan theta. So, but it's kind of backwards. Like yours is really x squared plus 1. Both your a and b's are 1, so it's your x is tangent of theta, and then obviously your x squared is tangent squared theta. Dx is secant squared theta. Messed that up bad last night. That's kind of the one issue, is that that's not really appearing in this, but let's just go with it for a moment here. So it would be integral x cubed over square root tangent squared theta plus 1. And then your dx is secant squared theta d theta. Okay. So this tangent squared theta plus 1, that's an identity. That's one of those trig identities. Like this part right here becomes secant squared theta, but then you have the square root of it. So you just get a secant. So you have integral x cubed over secant theta, secant squared theta d theta. Okay. And that one cancels with that one. And you're still left with this x. You can always go back over here and say, okay, well, x cubed is really tangent cubed theta. So you got tangent cubed theta secant theta, because you still got one left up. And now it's
Then now, yeah, okay.
now it's this other type, which that's why I think this one is too difficult to sort of give you on a final, but it's like it does become n is odd, you know, becomes this first one here. Okay, there is another way to do this with just a u-substitution, but it, like you said, it kind of pops out as being a trig substitution.
Right.
So just wish I could tell you what was on the test. That would be a lot better.
Well, I asked her, and she said the difficulty that were on the last 3 exams are going to be the same as this final exam.
Okay. Well, yeah, that just, I mean, all that tells you is you got the same style of questions, I guess. Okay, so here's another question that's, it is an integral, but it's a volume of a solid. So it says find the volume of the solid obtained by rotating the region bounded by x equals 1 plus y minus 2 squared and x equals 2 about the x axis. All right, so any idea how you might start this?
Would you solve for y?
Yeah, it's probably set 2 equal to 1 plus y minus 2 squared. Move that over. When you take the square root of both sides, you actually get two equations. You get y minus 2 equals 1 and y minus 2 equals minus 1. So you get y equals 3 and y equals positive 1. I mean, that's nice. One of the oddities here is when you have x equals it's hard to graph.
Yeah.
Like everything is reversed. I don't remember if you're allowed to use a calculator on this. I want to say
Nope.
you're not. Yeah. So and sort of like further make this problem complicated is you're going about the x-axis. So a lot of like stuff here, but y goes from 1 to 3. Like you're bound, like there's some sort of intersection here. Since I'm just grabbing this, I don't think you're gonna get like exactly this. But let me just get a picture here. So here's the y equals 1 and y equals 3. And then what happens is you've got a little, let me actually I'm gonna grab these here. You actually have one here at 2. And then also here. So you end up, it's just this little piece right here. And then the line x equals 2, like this is your region right there that you're finding. So once you can identify that, and this wouldn't be part of the test, but how should you revolve it around the x-axis here? The problem is that it's hard to solve for y here. So that means you have to use another method. You have to use the shell method. Okay, and that's probably all I want to say about this one, because I don't actually think you'll get anything like this.
Yeah.
So, but just as a reminder, like there's shell, there's washer,
Right.
other things like that. All right. This one we kind of did earlier. It's kind of a repeat, but just bring this up again. It was the first problem I showed you. How would you attack this problem?
Is it not defined as 0?
Yeah, x cannot be 0, so you have to actually break it up from -1 to b and do the limit as b goes to 0, 1 over x to the 4th dx plus integral b to 2, 1 over x to the 4th dx. This one actually also diverges. You would see that when you get going.
Why don't you put from -1 to 0? Is it because it can't equal 0?
It is 0, but you're supposed to take the limit as b approaches 0. Like,
Okay.
because you can never, you end up getting something later on where, I mean, the antiderivative here is -1 over 3x cubed. And when you're evaluating it from -1 to 0, like what you can't do is go -1 3 times 0 cubed, even though you think you can, like it seems reasonable. This is wrong. What's preferred is you to say the limit as b approaches 0, -1 to b, and it becomes -1 over 3 b cubed. So you're not actually evaluating at 0. You're taking the limit as b approaches 0, which is as a student, maybe you say, okay, like this is the same thing. It's not like it's math and math language. It's different.
Yeah.
Limit's different than actually evaluating it at a point.
Yeah.
So that's the distinction there for that. Okay, your college must do polar integrals in calculus 3, because none of them, we never covered any of them.
Yeah, we're doing polar coordinates. That's what we did last.
Oh, you did, but did you do any integrals, polar integrals?
I don't think. Maybe. Hang on. Let's see. Doesn't look like it, no.
Okay,
We just did convert polar points to Cartesian points.
yeah, okay.
Yeah, we didn't do
That's
anything
that.
wrong.
All right, take a look at this problem here, if you can. Give me kind of you look it over, maybe write a few things down, but give me what you think this would be. What is the integration method here?
U sub,
Okay, what would your U be?
natural log x.
Okay, and then du is 1 over x, which is nice because it's in there. So yeah, this becomes u squared over x, and then x du. So those cancel. Your u of 1 is 0. Your u of e is 1. I really like this question because it like, really like comes out nicely. It just becomes 1/3 u cubed, evaluate from 0 to 1. Like it looks complicated, but it
Yeah.
really like folds into a nice little thing.
Yeah, right.
I mean, that's my style. My style is like not necessarily tricks, but like, if you
Yeah.
identify it and make the right steps, like it becomes very easy. I mean,
I'm definitely better at identifying stuff now.
how about this one here? This one's a little more complicated potentially.
Would that one be U sub as well?
What would your u be?
X plus 1.
Okay. So I'm going to follow this through. So du is dx. This becomes the integral of x over the square root of u du. See how the x did not cancel?
Yeah.
And I'm not saying you're wrong. You're actually correct here, but there's something else to do. And that's why I wanted us to look at this problem.
Okay.
You really want x to go away.
All right.
So which of these has x in it?
The U.
This first one. So
Yeah.
so sometimes, I can't say how often, sometimes you solve for u or for x. Sorry, solve for x. So x equals u minus 1. Plop that in
Okay.
there. And then you also write this as u to the 1/2. So it becomes u over u to the 1/2 minus 1 over u to the 1/2 du.
Okay.
That's kind of important to like see this one there, because it is not a hard problem.
It's just doing that extra step
yes,
that you wouldn't usually think to do.
right.
Are there any problems on there that like with converging and diverging integrals?
I mean, this is, yeah, I mean, this is a good one for us to look at next, because it's a composition of two things. It's an improper integral, which does matter. It does matter. You're like, okay, well, does it even converge? So when it's infinity, you don't have to worry about what x cannot equal. We did a couple earlier where it was like 1 over x squared from -1 to 1. Whenever you're dividing by 0, that's way more worrisome than this. This one you just integrate this thing. So how do you integrate x e to the x? What is the approach for that?
I see u sub and I also see integration by parts.
It's an integration by parts. You could use a u sub as part of it.
I just don't think that negative x isn't like enough, I guess, is how I would say it.
It is like by the most like firm definition of a chain rule derivatives, this wouldn't be a u sub, but I mean, you can handle this as minus e to the minus x when you integrate. So your du is dx. And so you can apply the uv minus the integral v du. So this is x times minus e to the minus x. And then you're supposed to evaluate that from 0 to infinity. We'll get to that. Minus the integral of v du. So minus e to the minus x dx. And that's from 0 to infinity. So the correct way to do this part on the left, and that's why I'm showing you this, is again to do this limit as b goes to infinity. And it's really minus x e to the minus x from 0 to b. These two make a plus, so it's plus integral 0 to b e to the minus x dx. The antiderivative of this we already did, it's minus e to the minus x. And so you kind of pair these together and do the limit all at once. So you limit b goes to infinity, minus x e to the minus x minus e to the minus x from 0 to b. And then that last step is you actually have to put in the b. So it's minus b e to the minus b minus e to the minus b minus 0 e to the minus 0 minus e to the minus 0. And this is where this is the step where you're worried about convergence or divergence. So the problem area is not e to the minus infinity. It's this one right here. This is the problem. And you would write this, or you would think this, it's minus infinity e to the minus infinity. The e to the minus infinity, well, that's 0, but this minus infinity out in front, that's problematic. Because it's like, well, what is that? And if you haven't done this before, it's bad. So this one is actually okay because it is 0. So because anything times 0 is 0. And then this one, the second one becomes 0 also. This is also 0 because it's e to the minus infinity. So then you get down way down here. So 0 times anything is 0. Good. And then this last one is where you actually get your number. It's minus 1, but then this subtraction comes in. So all this just equals positive 1. So this one does converge.
Okay.
If you'd like, we can look at one of the ones that does not converge.
So with
for
the
comparison.
and the intervals are when you are doing a integral that converges or diverges, is the interval going to have an infinity in it?
No, it could be that one that I just mentioned was like minus 1 to 1 over x squared dx. Could have a 0 in it.
Okay. So I guess my question is how to like identify between just a definite integral and then
no, like it's really this. It's so this one after you do all the work, it's the limit as b goes to infinity minus 1 over x evaluated from minus 1 to b plus minus 1 to x b to 1. Okay, like after you find your antiderivative and split it up. So now we're gonna, I'm sorry, b goes to 0, not minus 1, sorry. So now we're gonna actually do that. Limit b goes to 0. So this first part is minus 1 over b minus 1 over minus 1 plus minus 1 over 1 minus 1 over b. So what happens when b goes to 0 right there? You get minus 1 over 0, which you're not supposed to write, but you're supposed to think. And any number, this diverges. This part right here. So since this diverges, the whole thing diverges.
Okay.
So let me try to help here. Things that diverge that you're looking for is the following. It's like e to infinity. That diverges. 1 over e to minus infinity. These are equivalent, you might see. 1 over 0 plus minus 1 over 0. 1 over 0 to some power. That would diverge. Things that converge that you might see, e to the minus infinity, 1 over e to the infinity, 0 over 1 plus minus 0 over x to n. Trying to think of all these possible ones, but this is kind of what you're looking for.
Or is it e to the infinity just 1?
No, e to the minus infinity is 1.
Oh, okay.
That one goes up forever.
Okay.
You know, x to infinity, that's also bad. Okay. Here's go ahead.
So it's a definite integral, and just do it like a regular definite integral. If
Well, you have to find the breakpoint where it becomes 0.
so since 0 is in the interval of that problem, it's in between -1 and 1.
So, but it, like, let me give you another one here. It doesn't have to be 0. So it could be the integral from 2 to 4,
Right.
1 over x minus 3. And you have the same
And
problem.
since 3 is in that interval,
Yes.
then you do okay.
Then you have to break it apart.
Right, okay.
That just reminded me of, I guess, another one. You know, natural log of infinity. That's another one you might see. That also diverges. Okay, so here's another problem, kind of related. I'm jumping around a little bit. So part A is to find the area of this integral of this area into the curve. Okay. But let's just say, you know, Matthew changed it. He came along and said, no, that's no good. Your part A, Trenton, is cross sections, sides equal to the height, like whatever this is. That's your area, and we want the volume of this. So from last night, we talked about this a little bit. Do you remember how to find the area function in this case?
I do not.
So this is the side length. The side is 1 minus x to the 4th. And so is the other side. So the area function is 1 minus x to the 4th times 1 minus x to the 4th. So your volume is the integral from -1 to 1, the left and right bound, but you need to get your area function in there. This is that one on your exam where you cubed it rather than squared it.
Yep.
Because you just find the area of the square. And then the dx is that third dimension. You know, it's like base times height times width.
Right. Okay.
All right, so here's kind of your classic arc length problem where you just set it up. You don't actually do it because most of them you can't.
Yeah.
So the arc length has a formula. It's the integral of ds, and ds is the square root of 1 plus dy dx squared. So I think in structures like this, because you have to remember how to take a derivative, your y prime is 1 over sine x. Derivative of sine is cosine. So you could write this as cosine x over sine x. You could also write it as cotangent x, like that. And then you got to square it. So your y prime squared is cotangent squared x. So your arc length, sorry, that's wrong. It's not y, it's your arc length. Your arc is the integral from pi over 6 to pi over 3, because that's given. Square root 1 plus cotangent squared x dx. I don't recall if that's a trig one or not. Let me look. It says to just set it up. I mean, but the question is like, where do you stop? Where do you feel like, okay, I've set it up to the point that it works? This one actually is cosecant squared. So like, it's kind of like, well, where do you stop? Because it becomes the square root of cosecant squared x dx. And those definitely, you get that, you just get a cosecant x dx, which does have a known antiderivative, but this one says to stop there. I guess that's another point, is to make sure you know all the antiderivatives and derivatives, really well.
Yeah.
If there's any confusion, it'll just mess up all the problems you're doing.
Right.
I mean, this one is not a known one, but I'll just write it anyway. Cosecant x minus cotangent x. It's weird because they want you to, they give you limits, like as if you're going to evaluate it.
Yeah.
Anyway, okay. Let me go see what else I could find. Looking at another one. We've already covered all these. All right. Yeah, so that's 10 minutes here. What I'm still looking here. Do you have anything you're seeing that you want to look for?
I got a midpoint rule.
Okay. What's do you have a function for it?
Yeah, it's integral from 1 to 3 of natural log x.
1 to 3. How many ends do you have?
4 rectangles.
4. Okay. So we'll start with delta x. Delta x is b minus a over n. So that's 3 minus 1 over 4, which is 1/2. And then my preference is to write the left bound and then add the delta x. So this would be 3/2, add a 1/2, that's 2, add another 1/2, that's 5/2. And then you stop and you get there. This is truly beneficial for midpoint because you literally need the midpoint between 1 and 3/2, which could be a little hard. In this case, it might be better to write it as decimals just to kind of like not get
Right.
fraction issues, but it's 1.25, 1.75, 2.25, and 2.75. And these are the numbers, like the rest you just throw away. But the midpoint rule says you take your delta x and multiply it by f of 1.25 plus f of 1.75 plus f of 2.25 plus f of 2.75, like this. And then in terms of your numbers, well, it's 0.5, and then your function is natural log. So it's natural log of 1.25 plus natural log of 1.75, natural log of 2.25, and so on. It's the only,
So you just take the literal midpoints of everything and just plug
the
it in.
averages. Yeah, but you got to get these.
Okay.
You got to get these points here. Now, notice that there's 5 points, even though there's 4 rectangles, because like 4 left, 4 right, and then the midpoint, there's truly only 4. Like if I were grading stuff, I would definitely make sure a student only had 4 rectangles, because that's a big indicator of like, do you understand this or not?
Right.
There have to be 4 rectangles because I told you there's 4 rectangles. But it's literally a midpoint, like if you're if you're struggling for time, maybe just write it out. Like this one you cannot evaluate, but like, let's say it was like an x squared with fractions. You might just leave that till the end for analysis, because it's just could take too much time potentially.
I got to interval converging and diverging problems.
Okay.
And it's the integral from 1 to infinity of 3 over 2x minus 1.
Like this.
Yep.
Okay. And so like I can tell you that this one diverges because it's the x to the p, and the p here only if it's greater than 1 does it converge.
Right.
But we'll go through it. So the antiderivative of this is 3/2 natural log absolute value of 2x minus 1. Like that's, you got to be able to do that whether it's an improper or not. So just we'll stick that to the side here for a moment. It's the limit as b goes to infinity, integral 1 to b 3 over 2x minus 1 dx. And then you find your antiderivative like I mentioned here. So it's limit b goes to infinity, 3/2 natural log absolute value 2x minus 1 from 1 to b. Notice that the 2x minus 1 equals 0 and x is 1/2. And this is outside the a to b. So you don't have to worry about it. Like,
okay.
They could really, really mess with you guys by incorporating both. So this is 3/2 natural log 2b minus 1 minus 3/2 natural log 2 times 1 minus 1. The one with the number in it, you almost never, like you don't even need to deal with that until you figure out whether this part converges or diverges.
All right.
Okay, so this part right here, this is really what all it comes down to. And this is one of those natural log of infinities that I wrote earlier. This one diverges.
All right.
I guess I can add to that list here. This is really an obscure case, but I'll throw it in there. The arctangent of infinity and arctangent of positive infinity. These also do converge. This one's minus pi over 4. This is pi over 2 and positive pi over 2.
And then
So
the
you
other
had
one, the other one is integral from 2 to 5 of x minus 2 to the negative 1/3.
Like this?
Yep.
Okay. Yeah, so the issue is at 2, because another way to write this is it's the cube root of x minus 2. So when x is 2, you get 1 over the cube root of 0. And that's bad. That's obviously a problem. So that's why it's an improper integral. So you would go limit as b approaches 2, integral b to 5. Okay, and you got to be comfortable finding your antiderivative. So you add 1 to this, that's 2/3. And then you divide by the new exponent, but when you divide by 2/3, it's the same as multiplying by 3/2. So you get a 3/2 there. Notice it's the flip of the exponent there. And you want to evaluate that from b to 5, limit as b approaches 2. So you take the limit as b approaches 2, 3/2, 5 minus 2 to the 2/3, minus 3, that's the wrong spot, 3/2 b minus 2 to the 2/3. And again, the one with the numbers in it, like don't even look at that. Just go over here. You got to figure out whether this diverges or converges. That's really important. So as b approaches 2, let's just say it is 2. Like if you remember all the way back in calculus 1, like the first thing you try is just putting the number in. And it's different when it's 2 versus infinity. Like when it's a number, you can just plop it in. So 2 minus 2 is 0. 0 to any power is 0. 3/2 times 0. So this is okay. This one actually converges.
Converges to 0.
Yes.
Right.
But the whole integral becomes 3/2 3 to the 2/3 power.
Oh,
Like, this
so
is your final answer.
it converges to that, not 0, right?
Yeah, not 0. Like this one on the right, it converges and it converges to 0. Like, but the important, this is really important, is when you get a number, you can literally put it in. When you get infinity, you have to decide what happens as that number gets large or really small.
Yeah. Right. Alrighty.
Okay.
Like last
You could
semester, it was easier for me to. It's easier for me to learn at the end of the semester than it is at the beginning.
Yeah. You did. I think if you really understood what we did today, I mean, that's pretty much the culmination of all this. Is like,
Yeah, I just need to practice.
Yes. All right. Well, thanks so much for all your scheduling. I'll send you the notes here shortly, and good luck on your exam. I think you'll do great.
Alrighty, thank you. I'll see you
Great,
next
man.
semester.
Sounds good. See ya.
See ya.